What are some of the challenges associated with relying on cloud-based language models for function calling, as mentioned in the paper?
Some of the challenges associated with relying on cloud-based language models for function calling, as mentioned in the paper, include substantial costs, privacy concerns, and the need for continuous Wi-Fi connectivity. The cost of using large language models like Google's Gemini family models and OpenAI's GPT series models can be significant, with interactions with an AI bot costing around $0.24 United States dollars per hour according to the GPT-4 API price. Additionally, the inference costs for function calling with traditional retrieval augmented methods can amount to approximately $0.01 USD per call, which can accumulate significantly in practical applications involving multiple function calls. Privacy concerns also arise due to the potential exposure of sensitive information when relying on cloud models like GPT-4. Moreover, the reliance on cloud-based models necessitates a constant Wi-Fi connection, which can limit the accessibility and usability of AI agents in scenarios where internet connectivity is unreliable or unavailable.
How does the proposed method aim to address the challenges of cost and privacy associated with using large language models like GPT-4 for function calling?
The proposed method addresses the challenges of cost and privacy associated with using large language models like GPT-4 for function calling by developing a method to enhance both accuracy and latency for function calling on 2B parameter models on devices, achieving state-of-the-art results. This approach involves tokenizing the core function's name and fine-tuning the model with functional tokens, allowing the model to understand software application capabilities with additional special tokens, learning to map function descriptions to specific tokens. By fine-tuning the model to understand the significance of functional tokens, it can conduct inference by employing the added special token, less than nexa_and greater than, as the early stopping criterion, reducing the number of tokens needed to accurately identify a function name. This strategy significantly diminishes the inference costs associated with large language models like GPT-4, enabling 37 times more function calls with the same battery on an iPhone and reducing latency by approximately 35 times per function call. Additionally, by incorporating numerous special tokens into the tokenizer and expanding the language model's head, the method utilizes a weighted cross-entropy loss as a surrogate loss to improve convergence, addressing the imbalanced dataset challenge during model training and aiding in cost-effective training. This innovative approach not only enhances the efficiency and affordability of function calling, but also mitigates privacy concerns by reducing the reliance on cloud-based models and enabling deployment on edge devices like smartphones, thereby offering users a solution that balances speed, accuracy, cost, and privacy considerations.
What is the main motivation behind developing a method to enhance accuracy and latency for function calling on 2B parameter models on devices, as stated in the paper?
The main motivation behind developing a method to enhance accuracy and latency for function calling on 2B parameter models on devices, as stated in the paper, is to address the challenges faced by edge computing-based models, such as slower latency, limited battery life, and the need for continuous interaction. By fine-tuning the model with functional tokens and tokenizing the core function's name, the approach aims to improve both accuracy and latency for function calling on devices. This method allows the model to understand software application capabilities with additional special tokens, enabling it to map function descriptions to specific tokens and achieve better performance in function calling compared to larger models like GPT-4. The goal is to save context length during model inference, enabling more function calls with the same battery and reducing latency per function call significantly. Ultimately, the objective is to enhance the efficiency and effectiveness of function calling on edge devices like smartphones, cars, VR headsets, and personal computers, making the deployment of AI agents on these devices more practical and cost-effective.
Can you explain the significance of tokenizing the core function's name and fine-tuning the model with functional tokens in the proposed method?
Tokenizing the core function's name and fine-tuning the model with functional tokens in the proposed method is significant because it allows for the accurate selection of the appropriate function from a pool of available options and the generation of correct function parameters. This process involves a two-stage approach. First, understanding the function's description and arguments based on the user's query, and then creating parameters for executing the function. By assigning unique functional tokens to each function in the pool, the model can classify the correct function name among these tokens, simplifying the prediction task and reducing the number of tokens required. This method enhances the accuracy of function name prediction and minimizes the tokens needed for identification. Additionally, fine-tuning the model with functional tokens enables it to learn the importance of these specialized tokens, improving its ability to select the correct function. This approach streamlines the inference process by using a special token as an early stopping criterion, eliminating the need to process function descriptions and reducing the tokens required for accurate function name identification. Ultimately, tokenizing the core function's name and fine-tuning the model with functional tokens optimizes the function calling process, leading to better performance in function selection and parameter generation, as demonstrated in the study.
How does the model use functional tokens to achieve better performance in function calling compared to GPT-4, according to the paper?
The model uses functional tokens to achieve better performance in function calling compared to GPT-4 by designating unique functional tokens to represent available functions, ranging from less than nexa_0 greater than to less than nexa_n1 greater than. This approach transforms the prediction task for function names into a single token classification among the n functional tokens, enhancing the accuracy of function name prediction while reducing the number of tokens required. By introducing these special tokens into the tokenizer and expanding the language model's head by an additional n units, the model can pinpoint the correct function among the n functional tokens through argmax probability selection during function name prediction. Additionally, incorporating function descriptions into the training dataset enables the model to learn the importance of these specialized tokens, enhancing its understanding of the associated meanings. This methodology allows the model to conduct inference by utilizing the added special token, less than nexa_n greater than, as the early stopping criterion, eliminating the need to analyze tokens from function descriptions and significantly reducing the number of tokens required to accurately identify a function name.
What is the key difference between the conventional retrieval-based method and the proposed model in terms of function name prediction accuracy and token usage?
The key difference between the conventional retrieval-based method and the proposed model in terms of function name prediction accuracy and token usage lies in the approach to predicting function names. The conventional method requires generating multiple tokens to form one function name, which can lead to inaccuracies. In contrast, the proposed model designates functions as unique functional tokens, assigning token names to represent available functions. This transforms the prediction task into a single token classification among the functional tokens, enhancing the accuracy of function name prediction while reducing the number of tokens required. By introducing special tokens and modifying the model architecture to accommodate these functional tokens, the proposed model achieves better accuracy in function name prediction with reduced token usage compared to the conventional retrieval-based method.
What is the dataset collection process outlined in the paper for fine-tuning the models, specifically focusing on Android APIs?
The dataset collection process outlined in the paper for fine-tuning the models, specifically focusing on Android APIs, involves gathering 20 Android APIs categorized into system-level functions, app APIs, and smart device management APIs. The selection criteria include usability, usage frequency, and technical implementation complexity. The APIs are organized into 3 categories to ensure realistic execution on devices through Android app development, provided the necessary permissions are available. The dataset generation process consists of 3 phases: generating relevant queries and function call arguments, developing irrelevant queries with suitable function bodies, and implementing binary verification using Google Gemini. Positive queries are created to be resolved by a single API, and Google Gemini API calls are used to generate function call arguments. Negative samples are included to enhance the model's analytical skills. The balance between positive and negative datasets is maintained with a ratio of frac m/n, where m and n are both set to 1000. Additionally, a verification mechanism is introduced to evaluate the completeness and accuracy of generated function calls, triggering a regeneration process if necessary.
How does the paper describe the process of generating relevant queries and function call arguments for dataset creation? And why is it important to include negative samples in the dataset?
The paper outlines the process of generating relevant queries and function call arguments for dataset creation by emphasizing the importance of formulating well-defined queries and accurate function call arguments. The strategy involves generating positive queries that a single API can resolve, utilizing predetermined API descriptions to produce the required function call arguments through subsequent Google Gemini API calls. This method ensures that the dataset comprises queries that align with the function's capabilities, enhancing the model's ability to accurately select and execute functions based on user queries. Additionally, the inclusion of negative samples in the dataset is crucial to improve the model's analytical skills and practical application. By incorporating examples from both positive and negative datasets, the model learns to differentiate between correct and incorrect function call arguments, thereby reducing errors such as missing arguments, incorrect argument types, or misinterpretations of queries. The balance between positive and negative samples in the dataset is essential for training the model effectively and enhancing its overall performance in generating accurate function calls.
What are the key training methodologies mentioned in the paper for model development, and how do they differ in terms of optimization techniques and parameters?
The key training methodologies mentioned in the paper for model development are full model training and LoRa model training. In full model training, an Atom W optimizer with a learning rate of 5e5, a warm-up step of 10, and a linear learning rate scheduler are utilized. The same optimizer and learning rate configuration are applied to LoRa training. In LoRa training, the LoRa rank is set to 16 and LoRa is applied to specific modules such as Q_project, K_project, V_project, O_project, up_project, and down_project, with the LoRa alpha parameter set to 32. Both training methods involve setting the number of epochs to 3. The optimization techniques differ in the application of LoRa, which is a form of low-rank adaptation that enhances the model's adaptability to specific function setups. LoRa training focuses on optimizing specific modules within the model to improve performance, while full model training encompasses training the entire model with a standard optimizer. The parameters, such as the learning rate, warm-up steps, and LoRa rank, are adjusted to suit the respective training methodologies, ensuring efficient model development and training for accurate function calling.
Can you explain the experimental evaluation conducted in the paper to compare the model's accuracy and response time with premier models like GPT-4 and GPT-3.5?
The experimental evaluation conducted in the paper compared the model's accuracy and response time with premier models like GPT-4 and GPT-3.5 by initially benchmarking the model against these established models. The study focused on assessing the effectiveness of the model in generating accurate function calls. The evaluation involved comparing accuracy and response time metrics. The RAG technique was employed to reduce incorrect outputs and latency by providing concise function options to the language models. The integration of Meta's FAISS for semantic search, enhanced function call description retrieval. The impact of training dataset size and model training methods on performance metrics was also analyzed. The evaluation extended to Android system function calls, where the model's accuracy and latency in function call generation were scrutinized. The study included a comparison with GPT-4 and GPT-3. 5. Showcasing the model's performance improvements in accuracy and latency. The Octopus model was also introduced, demonstrating exceptional accuracy and reduced latency, especially when deployed on mobile devices. The evaluation further expanded to include Vehicle, Yelp, and DoorDash function sets, highlighting the model's adaptability across various domains. The study emphasized the importance of dataset size in training the model efficiently and the utilization of LoRa training for diverse function setups. Additionally, the paper discussed the weighted loss function for special tokens to address imbalanced datasets during training. The results indicated that the model achieved high accuracy levels and reduced response times compared to premier models, showcasing its potential for deployment in various applications and environments.